first lecture will be, the title of the first lecture is Homotopy algebra and the non-commutative geometry.
Thank you very much for the invitation. So today I'd like to talk about these homotopy algebras, and so maybe first I'll explain how this some homotopy algebras. There are several homotopy algebras like A-infinite algebra or L-infinite algebra, C-infinite algebra, and so on. But let me just talk about A-infinite algebra today. So how they appear naturally in some mathematical physics. And second is what is then this A-infinite algebra. Third is why A-infinite algebra. So why we think this is a very good notion, and for so we take dual, and we go to some non-commutative algebras, and then I'll explain some more correspondences in this dualization. So first, let's discuss how these A-infinite algebras arise. So let me first talk about what's called two-dimensional topological field theory. So this with very scary name, but it's nothing but this correspondence. What is this? So for a circle, you correspond some vector space. And if you have a surface with boundary circles, then you correspond a morphism, some homomorphism. So if you call it sigma, then we get phi sigma in Hom V tensor 2 to V. So each circle corresponds to vector space. So you think of this as you have two inputs, and for each sigma we give one output. So think of this as some kind of operation. And what does this mean? So this topological means any surface which is topologically equivalent will give rise to the same map. So, for example, vector space. So, yes, so we say V is a two-dimensional topological field theory if we have this kind of vector space and morphisms and so on. So for example, if you have a surface like this, this should still give the same homomorphism because it's topologically the same. And then, so there is this obvious surface, which is one input and one output, and we require that this goes to identity morphism. And the last and most important thing is that if you are given several of these surfaces, and you can glue them. So, for example, you have one surface, and suppose you have another. Okay, maybe let's try another one. And there is this gluing operation, and it has to be compatible with gluing. So you can just glue. Then what you get is something like topologically looks like this. And we require that the maps corresponding to this figure actually also corresponds. So what this means is you think of this as two input, and then we have an output So that would be because of, if you say this is sigma, then so you have x and y, and you plug this into this homomorphism, phi of sigma, which corresponds to this surface, and then use this as an input and apply this another operation with another input z. So z, so phi sigma prime. Then, so this is, let's call this sigma double prime. Then we require that this equals sigma double prime of x, y, z. Okay, so so there are these operations corresponding to each Riemann surface with boundary circles, and all of them has to be compatible in this sense, on this gluing sense. And it's not hard to see, actually, if you play with this, then this two-dimensional TFT just means that V is algebra with inner product this is compatible inner product in the following sense, and this is actually called Frobenius algebra. This algebra. So what is the algebra structure? This pair of pants is this is the multiplication. So this is the multiplication, and this guy actually has to be same as composing in the other way. So you can compose first y and z, and then you can compose y and z first and then x, or you can compose x and y first and then z. But topologically, when you glue, that always has to be same as this. So what that means is this multiplication satisfies this associativity. And this guy, the inner product, this is the inner product because this is supposed to be an element in Hom of V tensor 2 to V tensor 0. But what is V tensor 0? That's just field, base field. So this is Hom V tensor 2 to K. And then this gluing operation, let's see what this gluing operation means. You can first multiply and then take inner product. Actually, maybe I should just close it off here. So you can, if you just make this into an inner product, then the same compatibility holds. And what that means is you can first multiply and then take inner product with z. It should be equal to first multiply y and z and take inner product with x. Okay. So it's an inner product, but it has to be compatible in this sense.
It's a good question. So far, what I don't quite see is why we don't really use points and graphs and trees rather than surfaces.
That if you use points and lines, then that would be one-dimensional topological field theory. So I mean, in general, I mean, what do you mean? And there would be n-dimensional TFT and so on. But certain theories, I mean, it depends on what kind of theory you are working with, right? I mean, some theory is two-dimensional TFT, and some theory is three-dimensional TFT, and so on. Okay.
Does it make any difference? I don't see any difference between one dimension and two dimension.
Right. I mean, so this because it's more fun. In general, I mean, you can. Yes. So there is this phrase that QFT, quantum field theory, is just a functor from cobordism category to vector spaces. So this is important. Quantum field theory, which I don't know what it's about, but just a functor from cobordism category to vector spaces. But anyway, so we have TFT, then actually these cobordisms are considered up to topology. And
could you draw that compatibility in a
this one,
so
this one is, so you multiply x and y. And then inner product is this. So, and this should be same as first multiplying and then taking inner product. So now you can try what's called open two-dimensional TFT. So what does open mean? Open means now not only this kind of surfaces with boundary circles, we will consider surfaces with boundaries and intervals. So instead of circles, we'll have intervals. So interval, then this will go to a vector space V, and we'll have some this surface with boundary.
You also consider the map from the smaller number of surfaces to larger number of surfaces.
Yes. So that, yeah, it's all allowed, but because of compatibility, it's just you can just decompose them into these basic pieces, and so these morphisms and so on. And if you do it up to topology, then it's almost the same, actually. But so actually, it's more interesting if you consider you put C here. So what is C? So C is for conformal. So what this means is that instead of just looking at this as a topological surface, we'll consider it as a Riemann surface. So if their complex structure is different or conformal structure is different, we're going to regard it as a different surface. That means we'll have a lot more morphisms than before. So in this case, so actually it's much better to just contract. So we'll contract. I mean, this interval is some figure. I mean, it's some symbolic thing. It doesn't really mean interval. So we can just make it into a point. And all this into a point. Then what you get is a circle with bunch of points. Well, in general, I mean, you can have some higher genus surface like this, but let's just consider for simplicity just genus 0 on its disk. So, okay, so in this open TCFT, so what this means is for a point, so we associate a vector space V, and for this moduli space of configuration of red points on a disk, we'll okay, so we'll consider this moduli space. space. And if you just consider moduli space, that would be just conformal field theory, not topological. Then what is topological? We do, in topology, what we do is this, take homology and cohomology. Sorry. So, I don't know, it's spam. Sorry. So to become a topological conformal field theory, we need to take homology or chain complex of these things. So you take chain complex of this thing, and so on. So, and then it will correspond to a morphism. So this is a bit strange. So let's first consider some minute what does this moduli space really looks like. So in the case of 3 points, then we know that from undergraduate complex analysis course that we can always send any 3 point on a disk into fixed 3 points. Let's say 1, -1, and I, minus I. Okay, so that means it's biholomorphic to this. So if you call this as M3, moduli of 3 red points, then this would be just a point. Because there is only, any configuration can turn into a fixed configuration. So it's just a point. And if you consider 4 of them, then now we can still send 3 of them into fixed position. Now 1 of them is free. So this is free, and the other 3 is fixed. So that means the moduli space is just an interval because this guy moves around here, right? So this M4 is just an interval. Now it gets interesting if we consider 5 points. Then, okay, we still fix 3 points here. And then 2 points are free. So we have 2 points which are free. So let's call it X and Y. So it's really a moduli space of X and Y on an interval. So think of it this way. So we have an interval from 0 to 1. And there is this 2 red point, X and Y. And we require that X is always smaller than Y. Okay? So we're really looking at the configuration space of this kind of set of point. The configuration space. And then you can actually draw them in a plane because this is X-axis, this is Y-axis. X equal to Y is here. And Y is less than 1. So the configuration looks like this, but actually it doesn't include the boundaries. So let me just erase slightly. Okay, and now what's interesting? What gets interesting? I talked about this in Kai several times, but what gets interesting is now we have to. When you compactify this, we actually use some different compactifications. So let's see how this goes. So you can just compactify it as a triangle, but that wouldn't be so interesting. So what you want is what people call Fulton-MacPherson type compactification. What this means is, so these 2 points will move around, and they might collapse to the point 0. And what we want is, when they collapse, we want to somehow record their relative speed. So it's like you have 2 Toyota cars, and they just speed up and crash at 0. And you have to, somehow tell who is more responsible, who collided first. Or did they collide first and then collide to 0? Or did X collide to the 0 first and then Y collide? Oh, there is Japanese here. So that was just, I'm sorry. Yes.
In your moduli space, your underlying set are just famous here without genus?
In this case, yeah, this case just disk. So disk with this red point, and so this up to automorphism of a disk, so it's up to automorphism, biholomorphic maps of a disk. So if you apply biholomorphic map of disk, you can always send any 3 points to fixed 3 points, and so the other points are not fixed. So you want to say, so the relative speed is important. So that's what Fulton and McPherson studied to compactify, considering all these relative speeds and so on. And as X goes to 0 and Y goes to 0, what happens is they approach this point, 0, 0. And their relative speed, you can record it as something like Y over X. Right? So it's the slope. So this slope is actually the relative speed. And to record the relative speed, you have to compactify this as, instead of a point, like a blow up. So you just blow up here. So instead of a point, you have this line, which records. So it's much easier to just draw it like this, so that you can actually look at the relative speed. So this line corresponds to this 1 point here. Also, as when they approach 1, you have to also consider their relative speed of collision at 1. So you also have to blow up at 1. Now, how about this point? At this point, there is no collision because X goes to 0. So this is X goes to 0, but Y goes to 1. So Y goes to 1 and X goes to 0. So there is no collision. So we don't need to compare the speed. So we get this pentagon. Okay, so this is M5. And you can keep going. And this is what's called Stashev polytope. So this Mn plus 1 is called Stashev polytope. And so in general, you can think of it as a compactification of moduli. This is moduli.
So M5 is moduli space?
Yes.
So you just use the same length.
This is moduli space, but you introduce different compactification. So inside is the same. The interior is.
You call it M5.
Yes. Sorry. So let me, maybe if you want, I can put bar as a closure or compactification. Compactification of moduli space of something like this: x1, x2. So Mn plus 1, there would be n minus 2 points. Okay, so you can think of this as this compactification. And if you think, what is codimension 1 boundary? of this moduli space. Now this will be some kind of polytope, something like this. Now we want to consider what is this face? Where is this face coming from? For example, this face is where x is equal to y. So codimension 1 face means the collision of this one collision. So x and y is the same, so it's one collision. And this codimension 2 face is 2 collision and so on. So in fact, codimension 1 boundary is some of them collide. So you can think of it as 0, x1, x2, xi collide with xi plus 1, collide with xi plus 2, xi plus k1 minus 1. I plus k1 minus 1 and xi plus k1 and xk n minus 2. Okay. So in the middle, they collide. So this is the typical codimension 1 boundary. Or I mean, it may collide with 0, but let's just regard it in the same way. But in this collision, there is still some moduli space. So you have to consider relative speed of collision. And then what you can do is you can think of this as the lower limit, and this is upper limit. So you just rescale this to be 0, rescale this to be 1, and there is this xi plus 1 star, this rescaled things, xi plus k1 minus 2 star. So what this means is, even they collide, there is still this, in this compactification, there is still this moduli, there are some choices, so there is this moduli space. So this guy, the boundary looks like this one moduli space, of lower indices, times, if you now consider this as 1 point, and then you have another big moduli space. So this may be written as a formula like like boundary of this m plus 1 is something like this guy, which is k1 plus 1 times, now if you consider this whole thing as a point, and then this big, the leftovers form another moduli space, so that's m k2 plus 1. It's the union of these kind of pieces. Okay, so now if you consider this chain complex of these things, which was this topological conformal field theory, and then here there is this natural operation of boundary, this boundary in this chain complex, singular chain complex, which goes to okay. So what corresponds to this is what we are going to call this n, which will be Hom from V tensor n to V. So we have this n plus 1 points. Here is n points, and here is 1. So the sum is n plus 1. You think of it as n of them as inputs and 1 of them as output, then you have, so TCFT means for each element here, you correspond a homomorphism. But there are several elements. Which element do we take? We take this fundamental chain. So you take fundamental chain, which is the polytope itself. And then this goes to this Mn operator. Now, what does this relation say? This relation, to be compatible, this says Mn, when you take the boundary of Mn, it should be sum of this Mk1, Mk2, sum of these kind of operations. Okay, so this is a bit, well, I mean, because of this phenomenon. But, I mean, it might take some time to really say this precisely, so let me just stop here and explain what the definition of A-infinite algebra. So A-infinite algebra is a vector space with sequence of operations satisfying the following equation: sum of x1, x2 for all xi in this vector space. You take some m operation first, and then take another operation for the rest of the leftovers, and this has to be 0. Okay, so the sum was not 0, but actually same as m1 of mn, but this guy you can actually move it to here. It's also of the same form, taking m twice. Okay, so let's look at, so this is true for any case, so let's look at the easy cases. So when you have only one input, x1, so what this means is you take m twice, so that means this is same as you take m1, which has only have one input, and you do m1 again, and this has to be 0. So the first equation means m1 is a differential, and when you have two of them, then the possibilities are like you can do in this way, or you can do this way, or you can do this way. So what this means is first take differential of x1 and then take product m2 of x2. So this k means just number of inputs. So m2 of x1, m1 of x2. Let me write it here. Plus this m2 of x1, x2 of m1 being 0. So this is nothing but Leibniz rule of product m2. m2 is the product, m1 is d. It's just, and I should do the next one, but because I don't have much time for other things. So if you do one more time, then what you get is homotopy associativity. So if you do x1, x2, x3, this thing, then you can first multiply x1, x2, and then x3, and so on. So this infinite algebra is not really a product, is not associative. It's associative up to some homotopy, and this homotopy is recorded in M3. And the next formula is homotopies for this homotopy. So it's sometimes called strongly homotopy associative algebra. So this is infinite algebra. Okay. Anyway, so naturally arise from this moduli space of points of a disk. And maybe I jump to why we why this infinite algebra. So the reason number one, this is my personal opinion. So okay. So yesterday, Professor Jin-Hyun Park spoke about DG categories, or I mean, if you have only one object, then you have differential graded algebra. So what's usually called DGA. So you have a differential and product and so on. But the real correct notion of equivalence, or you can have, I mean, you have DGLA, which is differential graded Lie algebra. But the correct notion of equivalence of these things are quite strange. For example, you have DGA1, DGA2 is equivalent if there exists DGA B1, BK, such that, so you have this kind of B1, B2, B3, B4, B2. So, I mean, this differential graded algebra may be equivalent even if you don't have any morphism from A1 to A2. But it's like, this is like derived category. You actually have a morphism going this way, and this way, this way, this way, and so on. So what this suggests is actually, because there is no morphism, actually one might need more morphisms to actually work with correct notion of equivalences. And this is what this infinite algebra provides. So we can just say they are equivalent if there exists an infinite map A1 to A2. So these are both DGAs. Then there is an infinite map. So differential graded algebra, you can think of it as infinite algebra. There is some kind of infinite map which is inducing isomorphism on homology. So what I mean, okay. So what this means is you actually have a real map from A1 to A2. But it's not a map of differential graded algebra, but it's some infinite map. So why this happens is you have this kind of arrows, and you can always actually invert as long as it's a quasi-isomorphism. So you can invert. I mean, there is always exist this homotopy inverse. This is something like Taylor series. If you have all Taylor series, you can, if you start from 1, then you can invert, right, by term. But if the DGA is like you have only 2 terms, like 1 plus x, or I mean, it's like 1 minus x, and so on. I mean, if you want to find the inverse, it's hard to find the inverse. But if once you allow all power series, and then you can find actual inverse, so on. So this infinite language is actually something like this. So instead of not just DGA, but the actual. MK is 0, so it's M1 is D, M2 is the product, and MK. Sure. Then it's DJ.
Is there some relationship between algebras and general operands?
So this polytope is called A-infinite operad. And
It does have operands.
so I mean, this operad is something like this times this V tensor K to V. Exactly. So you can really think of this, if you once fix this polytope, then you can think of this as some Hom from V tensor K to V.
This polytope is actually operand and
Yes,
the
polytope is
operand
Yes, polytope is operad, and you take the chain operad, and then induced operation is A-infinite.
Okay.
That's right. Yes. So one way to actually get non-trivial infinite algebra is the following, what's called homotopy, homological perturbation lemma. Let me just briefly mention. So if you have a differential graded algebra, so let's call A, then you have this homology of A, and you can take some representative homology so that it embeds into A. Then what you can do is you can actually, there exists this MK, this A-infinite structure which such that this homology with this MK isomorphic to A as A-infinite algebra. So, but here M1 is 0 because we are on homology. So what one can do is, if you have a differential graded algebra, you might have very complicated differentials. But you can actually get rid of all differentials, but there will be higher operations. So it's like, why do you need higher operations? In differential graded algebra, you might have some kind of messy products, some not just homology information, but some information lying behind homology, with some messy products and so on. And so this, to be equivalent, you have to somehow record this messy products and so on, which is recorded by these higher MK operations. Okay, and second reason I think is if you have an algebra. So I was going to talk about this a bit more, but because I don't have time, so maybe I'll just briefly say it. Then you can deform it. So you can deform A dot B into A dot T B. Deformed algebra. And the natural thing, so which is you have the original operation plus T times some linear bilinear map of these two inputs. And we want this, the new product defined in this, by this formula to be still associative. And then you can just check the associative equation, and what this tells you that something like this, phi A BC minus phi A times BC plus phi A B times C minus phi A B C equal to 0. I'm sorry, so this is equivalent to A dot TB dot TC equal to A dot T B dot TC. Okay. So we changed the original product into something with T, where T is infinitesimal, so we just set T squared equal to 0. Then the deformed algebra is associative if we satisfy this equation, and this means, if you, in homological algebra, it means this is a Hochschild second Hochschild class cycle of A, or the actual correct notation is HAA. Hochschild cycle. Okay, sorry, 2. So any infinitesimal deformation of algebra is, somehow can be captured by this second Hochschild homology. And the natural question is, what does first Hochschild homology or third Hochschild homology do? And that's actually capturing deformation into an A-infinite algebra. If you think of deformation into A-infinite algebra, then this becomes the full Hochschild complex. So this Hochschild thing actually is already looking at this A-infinite thing. Yes. And then infinitesimal deformation is associative. So because you have, it's a Hochschild cycle. Yes. No, it's a closed in Hochschild cohomology. So okay. So actually, to the easier language to actually consider this is what's called the bar complex. So this is just nothing but if you have V as a vector space, then you just look at tensors, all tensor products. Okay. And this is actually what is called core algebra. So this is a core algebra. That means we have an operation, this codifferential from TV tensor TV. Well, you have a bunch of tensors, x1 tensor, x2 tensor, xn. What this core multiplication do is just split into two parts. So x1 tensor of the xi. There is big tensor, so you just do. Maybe I should use color. So there are two kinds of tensors, and you just split one tensor into two tensors, xi plus 1, xn. Okay, so there is. And co-multiplication means you have this multiplication table, and then you just change the arrows, and then it's a co-multiplication in the co-algebra. And yes, sorry. And this MK was sending k tensors of vector space to V. Now you introduce notation like MK hat. This is a map from this tensor algebra to tensor algebra. And the way we define it is if we have map from x1 through xn, then you just take some part of it, sum of all tensors. So MK of. You don't take all of them, but just take some part of them and take sum of all possibilities. So then this is called MK hat. Hat means so every possible inputs. And this is what's called co-derivation. Co-derivation means it's compatible with this co-multiplication, and this it's just, you can just, when you divide, it goes into one of the two parts. So it's a bit technical language, but anyway, so this now A infinite, if you just denote M hat to be M k hat and sum of all k hats 1 to infinity, then A infinite equation is nothing but M hat composed with M hat being 0. If you think about this, because if you have inputs, then you take first some M operation of the middle, so that's this first M hat operation, and then you take the whole thing. So this actually doesn't have to take the whole thing, right? So this is actually stronger. So if you project to length 1 results, then that would be an infinite equation. But anyway, so that's somehow equivalent. Okay, so take M twice. So deformation of A infinite algebra would look like this. Instead of M hat, you would have M hat plus T phi hat, where phi hat consists of phi k hat, phi k is Hom V tensor k to V. So we are changing the mk operation by a little bit. Then M hat plus T phi hat, composition of M hat plus T phi hat being 0. So this means deformed, it's still an infinite algebra. In particular, it's still associative up to homotopy and so on. Then if you think about this, M squared is 0. So what you get is M hat composed with phi hat plus phi hat composed with M hat equals to 0. Because T multiplied with T is equal to identity. So this guy is what's called Hochschild. I mean, this is the general Hochschild cohomology. So Hochschild cohomology differential of phi is hat is defined to be commutator with M hat. So this means any A infinity formation is actually captured by this Hochschild cohomology of A infinite algebra. So in this sense, it's natural. Now, so
why is P hat and P hat composition is 0?
because we set T squared being 0, just to see infinitesimal deformations. Maybe I'll talk 2 more minutes, and we'll have break. So, okay. So because I have to talk about non-commutative things. So you have this tensor algebra, which is co-algebra. And you have this M hat, which is co-derivation with M hat composed with M hat, which is actually 1/2 of M hat, the bracket being 0. So then now you take dual of this thing. So this means TA star. Then you can imagine dual over co-algebra would be algebra. And dual over co-derivation would be derivation. Derivation in algebra is some kind of vector field. If you, take a differential manifold in the graduate course, then it's a vector field. And we'll call this vector field Q. And this relation becomes Q bracketed Q being 0. So actually, so let's say A is a vector space with basis EI, then the dual basis, let's call it Xi. Then what is this TA star? The dual, you consider all possible products of this dual basis. So this is kind of X1, Xn. So it's a formal. And because tensor is non-commutative, this is non-commutative, commutative power series. Okay. And this becomes formal. Formal means infinite. We allow infinite sum, as long as the length goes to infinity, because this is some kind of product, direct sum, and you take dual of direct sum, you get direct product. So you have to allow formal power series.
Do you allow associativity or not?
Yes, it's associative, because this is co-multiplication is associative. Co-algebra is co-associative. So this is associative. So this actually provides the easiest example of non-commutative geometry. So this is something like non-commutative geometry of a point. So if it's commutative, it's just Taylor series. So that means, so I already exceeded 2 minutes, but yeah, maybe I'll take a break and let's take 10 minutes break.